In this video, we're going to look at 3 problems that involve conservation of momentum. Pause the video now and try question 1. So as usual, a quick and easy diagram is usually sensible just so we can label things and be sure of what we're doing. So we have a car of mass 1200 kilograms colliding with a motorbike of 500 kilograms. This is stationary. This is moving with a velocity of 12 meters per second. And then after the collision, what is the velocity? And the combined mass is obviously going to be 1700 kilograms. So what we need to say is the momentum before is going to be equal to the momentum after. This is the conservation of momentum. So what is the momentum before? It's going to be m1 v1 plus m2 v2, and the momentum after will be the combined mass, because they stick together as we've been told, times by the combined velocity, which I'll call v3, but you could call v nu or vc for v combined. So mass 1 is going to be 1200 times by velocity 1, which is 12, plus, well, we could type this, we could calculate this, but we know it's 0 because this is 0. So plus 0, the combined mass, which is going to be 1700 times by the final velocity. So that should be an equal sign, which means that the final velocity, which I call v3, is going to be equal to 1200 times 12 divided by 1700, which is 8.5 meters per second to the right. We don't actually need to say that because we've got a positive velocity, which means it's still going in the same direction that it started in. Pause the video now and try question 2. So let's do a quick sketch. We've got the first train carriage has a velocity of 1.4 meters per second and a mass of 5,500 kilograms. The second is stationary and has a mass of 3,000 kilograms. After the collision, so this is before, this is after, the second carriage has a velocity of 1.6 meters per second, so it's positive, so it's going to be in the same direction as this. I mean, you could have done everything going left, but I just do everything going right. Habit, 3,000 kilograms, and then the first carriage, we're trying to find its velocity, and its mass obviously hasn't changed. So the momentum before is going to be equal to the momentum after. That's conservation of momentum. So the mass 1 times by velocity 1 plus the mass 2 times velocity 2, well, that's 0 because this is stationary. It's going to be equal to the mass of the first one times its velocity plus 3,000 times by 1.6. So if we solve this equation, we can find out what v is. And we see that the velocity is 0.5 meters per second. It's positive, so again, it's to the right. If it was a negative velocity, which sometimes you might get, it's rebounded off and gone left. If this mass was smaller than this, that's probably when you would find it would go to the left. Final question. Pause the video now and try question 3. So what have we got here? We've got a vehicle of mass 850 kilograms collides with a vehicle of mass 1100 kilograms. We had a velocity of 12 meters per second and a velocity of 5 meters per second. Both positive, so they're both in the same direction. And they stick together on impact. So this is before, this is after. So they've got a combined velocity mass of 1,950 kilograms. What is the final velocity? So again, it's very similar. It's basically identical to this problem here, except this is non-zero. So we can still say that momentum before equals momentum after. So 850 times by 12 plus 1100 times by 5 is going to be equal to the final mass times by v, which means that the velocity is 8.1 meters per second, and again to the right because it's positive. Part II now says, is the collision elastic? So an elastic collision means that kinetic energy is conserved. And an inelastic collision means kinetic energy is not conserved. So what we need to do is we need to work out the energy, the kinetic energy before and the kinetic energy after. So before, it's going to be half m1 v1 squared plus half m2 v2 squared. So we know what the mass and velocity of the vehicles are before. So we can type that into our calculator and work out the total kinetic energy. Which is 74,950 joules. The kinetic energy after is going to be half times the new mass times by the new velocity squared. Oops, type that in my calculator wrong. There's a divide where there should be a times. So we've got 63,969, which means there's been a loss of 11,000 joules. So it's inelastic. Some kinetic energy has been lost. And this is an important distinction. We must always have momentum being conserved, but kinetic energy does not always have to be conserved.